July 4th, 2012, scientists at CERN announced a discovery, the Higgs boson. The particle that gives everything in the universe mass. The room erupted. Champagne, tears, a Nobel Prize. But that same week, a handful of physicists ran the numbers. They plugged in the mass of the newly discovered Higgs, 125 giga-electron volts. And what they found made them stop celebrating. Because at that exact mass, the mathematics revealed something terrifying. Our universe is not stable. It's metastable, which means it's balanced like a ball on top of a hill. And at any moment, without warning, it could roll down. When that happens, a bubble will form somewhere in the universe. Inside that bubble, the laws of physics will be different. Atoms won't exist, chemistry won't work, stars can't burn, life is impossible. And that bubble will expand at the speed of light, consuming everything, erasing the universe, replacing it with something where nothing can exist. Why vacuum decay is dangerous? Because the universe could erase itself at light speed. To understand the danger, you need to understand what vacuum actually means. And most people think vacuum means empty, nothing there. But in physics, the even empty space isn't empty. Space is filled with something called the Higgs field, and think of it like an invisible ocean that fills the entire universe, every cubic centimeter, every void between stars. The Higgs field is everywhere, all the time. And when particles move through this field, they interact with it. Like moving through water, the field resists that resistance mass. Without the Higgs field, electrons would have no mass. They'd move at the speed of light. They couldn't orbit atoms. Atoms couldn't form. Chemistry wouldn't exist. You wouldn't exist. Now here's where it gets strange. The Higgs field has an energy state. Think of it like a landscape. The field can be at different values, at different heights on this energy landscape. When right now, the Higgs field is sitting in what we call a false vacuum. But there might be a lower energy state, a true vacuum. Down the hill, Dr. Leakin. When we measured the Higgs boson mass at 125 giga-electron volts, we could calculate the shape of the energy landscape. And what we found was unsettling. At that mass, the equations tell us there's likely another valley, a deeper minimum, which means our current vacuum state is not the lowest energy configuration. Now it's metastable, but like a ball. Balanced on a ledge, stable for now, but not the ground state. And in quantum physics, there's a phenomenon called quantum tunneling, where particles can spontaneously jump through barriers, even when they don't have enough energy to go over the top, which means the Higgs field could tunnel to the true vacuum spontaneously without warning, anywhere in the universe, at any time. And when it does, a bubble will form. The bubble starts small, smaller than an atom, but inside, the Higgs field has dropped to its true vacuum state. Lower energy, more stable. And in that lower energy state, the fundamental constants of nature are different. The electron mass might be heavier or lighter. The strength of the electromagnetic force might change. The strong nuclear force that holds atomic nuclei together might weaken, which means atoms as we know them can't exist. Electrons would spiral into the nucleus or fly away entirely. Depending on how the constants changed, chemistry becomes impossible, life becomes impossible, stars can't burn, galaxies dissolve. And here's the worst part. That bubble doesn't stay small. The true vacuum state is lower energy, which means it's more stable. And the energy difference between the false vacuum and the true vacuum is released at the bubble wall. This energy drives the bubble to expand at the speed of light. Light speed, which means you can't see it coming. The light that would warn you the bubble exists travels at the same speed as the bubble wall, and they arrive simultaneously. The first moment you'd know is when the bubble wall hits you. And in that instant, every atom in your body changes. You don't die. You cease to be made of anything that could be alive. You dissolve into subatomic particles that can't form anything. Vacuum decay is, in many ways, the perfect disaster scenario. The physics is so different that structures we depend on, atoms, molecules, even subatomic particles, may not be stable. It's not destruction, it's erasure. And once it starts, it never stops. It consumes the Milky Way, every star, every planet. Eventually, it would consume the entire observable universe, replacing it with a universe where the physics doesn't allow anything interesting to exist, just nothing. So, if this is possible, why hasn't it happened yet? The universe is 13.8 billion years old. That's 4.4 times 10 to the 17th seconds. And vacuum decay could start anywhere. The observable universe contains about 10 to the 80 cubic meters. So the question is, what's the probability that in any given cubic meter, the total number of chances vacuum decay has had to happen so far is about 10 to the -3, 1 in 1,000, which means we've been lucky. The dice haven't come up universe ends yet, but they could tomorrow or in 10 to the 100th years, long after every star has died, long after every black hole has evaporated. In fact, if vacuum decay takes longer than 10 to the 100th years to happen, the universe will die of heat death first. The expansion of space will spread everything so far apart that no new structures can form. Temperature approaches absolute zero. All activity stops. So there are two ways the universe ends: heat death, slow, cold, entropic, or vacuum decay, instant, total, complete erasure. The probability calculations are deeply uncertain. So, we can put bounds on it. We can say it's extremely unlikely in any given moment, but we can't say zero. And that's what's philosophically challenging about vacuum decay. It's not a matter of if, it's a matter of when. The question is whether when is tomorrow or 10 to the 200th years from now. And we genuinely don't know. So we exist in this moment, 13.8 billion years after the Big Bang, and in a metastable universe that could theoretically collapse at any instant. When CERN announced it was building the Large Hadron Collider, some people worried, could smashing particles together at near light speed trigger vacuum decay? After all, the LHC collides protons with 13 trillion electron volts of energy. In a space smaller than an atom, that's an enormous energy density. Could that energy be enough to push the Higgs field over the barrier to nucleate a bubble of true vacuum? If it did, the bubble would start at CERN, consume Europe. In minutes, the planet in hours, the solar system in weeks. Physicists calculated the risk carefully, thoroughly, and here's what they found: cosmic rays. Every second, high-energy particles from space slam into Earth's atmosphere. Some of these cosmic rays have energies 10 million times higher than anything the LHC can produce. Over the 4.5 billion year history of Earth, We've been hit by trillions of these ultra-high energy particles, and we're still here. Which means those collisions didn't trigger vacuum decay? If they had, Earth wouldn't exist to ask the question. And it's not just Earth. Like, the moon has been bombarded for 4.5 billion years. Mars, Jupiter, every planet in every solar system in the galaxy, cosmic ray omnipresence, is constantly hit by cosmic rays. If these collisions could trigger vacuum decay, the universe would have already ended. The fear about the LHC is understandable. We're doing something that feels unnatural, smashing particles together at incredible energies. But nature does this all the time. Cosmic rays hit our atmosphere with energies far beyond what we can achieve. They've been doing it for billions of years. If those collisions could trigger a catastrophic phase transition in the Higgs field, we'd already be gone. The fact that we exist is proof that the energies we're working with are safe, so the LHC is not going to trigger vacuum decay. Are too low, and nature has already run the experiment trillions of times, but that doesn't mean vacuum decay can't happen. It just means we can't cause it. It has to happen spontaneously, anywhere, anytime, for no reason other than quantum randomness. So, if vacuum decay can happen spontaneously anywhere in the universe, can we detect it? Could we see a bubble forming in a distant galaxy and track it as it approaches? No, because the bubble wall expands at the speed of light, and the light that would tell us the bubble exists travels at the same speed. So they arrive together. The first moment we'd know a vacuum decay bubble was approaching is when it hits us, and then we'd have exactly 0 seconds to react. You cannot stop a change in physics. You can't build a wall that blocks the Higgs field from changing state. Like, you can't deflect it, you can't shoot it down, you can't hide underground. The Higgs field fills all of space. A mile underground or on the surface, you're in the same field. Could you evacuate to another galaxy even if we had faster than light travel, which we don't? The bubble is expanding at light speed. You can't outrun light. So there is no warning system. No evacuation plan, no defense, no escape. If a vacuum decay bubble is heading toward Earth, we will not know until the instant it arrives. And then we'll cease to exist, not die, not be destroyed, simply cease to be made of anything that can exist. This is the ultimate existential threat. Not because it's likely, it's not, but because if it happens, it's total, unavoidable